Section 2.6 talks about moments and center of mass. Well, we want to figure out where to place our pin so that those will balance out. Wherever that's gonna be put, we call that X bar, the center of mass. Center of mass is where you place the pin, and then those two will balance depending on what M1 is and M2 is. So for this to work, if I placed X bar right there, then this distance times that mass should equal this distance times that mass. Remember, if you want to find distance horizontally, you always take right minus left, always. And this way you don't need the absolute value. And this will be X bar M1 minus X1 M1. Remember, M1, X1, X2, M2 are given. Of course, in physics, sometimes they give you the center of mass and they have you find the masses. So, you could play with that algebraically, but in this book, we're going to go straight forward. No tricky engineering stuff. Now I'm trying to solve for X bar. If I factor X bar out, it turns out if I really want to find the centroid, or the center of mass, that is X sub 1 M sub 1 plus X sub 2 M sub 2 divided by M sub 1 plus M sub 2. And if I want to write that in summation notation, that's how it looks. Basically, it's the sum of the distance times the masses divided by simply the sum of the masses, and that's what this is saying. Now let's just stick with this. X bar is the sum I equal 1 to n X sub I M sub I divided by the sum I equal 1 to n of M sub I, assuming you have n of those. All right, well, let's play the game. One dimension is fairly simple. This is how things work. Now, of course, assuming you're starting at the origin. So suppose we're talking about 0, 1, 2, 3, 4, 5, 6. Mass 1 is 2, and it is 1 unit away. Two units away. And I mean 2 units. X2 is 4 units, and it's 2. So the question is, where do you put the pin so that when you let it go, it balances out? Basically, you're looking at this. Oops. This has a mass 2, and this has a mass 4. And assume like a seesaw, where should you balance that out? Well, the way it works, X bar turns out to be the sum of X sub I M sub I, something we're going to get used to. If I don't write those, that means you just start with the first and you keep on going until you reach the second over the sum of M sub I. That would be 1 times 2 plus 4 times 2 I should put them in the right order. Mi. So it is 2 times 1 plus 4 times 2 divided by 2 plus 4. That turns out to be 8, 10, 6. So x bar should be 5/3, which is 1 and 2/3. If I move 1 and 2/3, that's where I would put the pin so that this is balanced out. Another example, I have the same mass, but I'm going to put that at different spots. So 0, 1, 2, 3, 4, 5, 6. I'm going to put 1 right here. One right here. They're all the same. No need to write 3. 1 at 2. And 1 right here. Now the question is, where should I put the pin to balance all of these out? Well, x bar is the sum of m sub I x sub I divided by the sum of m sub I. Again, I equal 1, 2, 3, 4. I equal 1 to 4 in this case. Well, we know what that is. That is, so they're all the same, right? So that's going to be 3 times 0 plus 3 times 1 plus 3 times 2 plus 3 times 6 over 3 plus 3 plus 3 plus 3. And that turns out to be 18, 21, 28 divided by 3, 6, 9, 12. That's 27. Made a mistake. So basically you factor the 3 out, 1 plus 2 plus 6, over factor the 3 out, 1 plus 1 plus 1, 6, 7, 8, 9, 27 divided, or simply 6, 7, 9 fourth if you reduce it. And 9 fourth is 2 and 1 fourth. So I would put the pin 2 and 1 fourth. I would put the pin right there, and those will balance out. And that's pretty much what we're doing. Now on 1 dimension, it's kind of straightforward. 2 dimensions, the trend follows. I don't make this a lot more challenging than it is. So basically when you have 2D, x1, let's say, well, we figure out x bar, let's say it's right there. We figure out y bar, let's say it's right there, and we say, hey, guess what? That's the center of mass. That's the center right there. Well, the way it works, again, if we're talking about discrete values, x bar, we already know what that is. That is the sum of m sub I x sub I divided by the sum of m sub I. And y bar would be the sum of m sub I y sub I divided by the sum of m sub I as well. So straightforward. Suppose we're talking about this and we're taking 1, 0. So let's say that's 1, 1. Now 1, 0, we're putting a mass right here. And that is 1. And 0, 1, we're putting a mass right there. And that is F4. Well, we know that the sum of m sub i's would be simply 1 plus 4, which is 5, so that's fixed. Now x bar is going to be the sum of m sub I x sub I over 5. That is 1 times 1 plus 4 times 0 over 5. That's 1/5. So this is 1/5 is about right there. And if I take y bar, that is the sum of m sub I y sub I divided by 5 again. That's going to be 1 times 0 plus 4 times 1. That is at 4/5. 4/5 is about right there. So that would be the centroid or center of mass. That's where you put the pin. Take this plate and if you turn it on its side, it will balance out. Now, what if we have not a fixed region, it's varying? There is a typo. A row should be in there. A row should be in there. And row should be in there. Of course, it's a constant, doesn't really matter. Now, on a test, I will provide this formula for you. You really don't need to memorize it. Now, suppose we're talking about a lamina. So let R be the region bounded above by a continuous function of f of x. So let's say we're talking about let's make it a bit creepier. Here we go. Let's say we're talking about f of x and g of x, and we're trying to figure out the centroid between A and B. So we're trying to figure out where should we put the pin in there so that this will balance out. It turns out, I used to derive this back in the days, but there's no point. X bar, now it is kind of the same analogy as we showed before. It turns out it is 1 over the mass times the integral of rho times x times f of x dx, that simple, and y bar is 1 over m times the integral of rho from a to b, of course, rho times f of x squared over 2 dx. Again, I used to derive this back in the days, but you barely see any application of it. And if we have, this is if you have just one of those. But if you're having this case, which is really what we're going to play with, it turns out the formulas are modified. Oh, and I forgot to mention, mass is simply the integral from a to b of rho f of x dx. So here it is with two functions, f of x above and g of x below, from a to b. Again, I'll provide that in your test. You don't need to memorize it. And I'm trying to figure out where do you put the pin so that when you lay that lamina on its side, it balances out. There's an assumption here that you will deal with this assumption on a broader application when you get to third semester calculus. So here we go. For the following exercise, compute the center of mass. They only want x bar in this case. So let's look at that and see how that works. If I just wanted x bar, well, x bar according to the formula is 1 over m, the integral of rho times x times f of x dx, where m is the integral of rho times f of x dx. And that's all there is to it. So in our case, this, let R be the region bounded by above by f of x, x left, the right, a of b, let rho equal the density associated with the lamina, the mass of the lamina, there it is, and the centroid is right there. Well, in our case, they didn't give us f of x, so we're assuming f of x is 1. So this is the integral from -1 to 3 of 1 dx. And that turns out to be simply x evaluated from -1 to 3. That is 3 plus 1, that's 4 units. And if I take x bar, that is 1 over 4, the integral from -1 to 3 of rho times x. F of x is 1 in this case. If they don't give you f of x, then that's the assumption. So that is 1/4 x squared divided by 2 evaluated from -1 to 3. That is 1/8 into 9 minus 1. That turns out to be simply 1. All right. And if we're talking about rho is a radical, well, we know that m equal the integral from 1 to 4 of the square root of x. Again, there's no f of x, that means it's a 1. That's x to the 1/2, add 1 to the power, divide by that. Substitute the 4 in. Square root of 4 is 2 cubed, that's 8 minus 1. And I'm getting 7/14. Not a very nice number. Most of the time it's not. And if I just wanted to find x bar, that is 1 over m. And the same deal, the integral from 1 to 4 radical x times x dx. That is 1 over a fraction is the reciprocal of the fraction, and that is x to the 1/2 times x to the 1, x to the 3/2 dx. Add 1 to the power, divide by that. So here 2 divides that 7 times. That is 3 over 35 times, if you put the 4 in, square root of 4 is 2. 2 to the 5th, that's 32. Minus 1 to any power is 1. That is 3 over 35 times 33. That is 31. That is 93 divided by 35. All right. Now, if rho equals 7 and we're talking about a square, where we're going to go, density is 7. Find x bar, y bar. Well, m is the integral from 0 to 1 of 7 times 1 dx, because here y equal 1. And that turns out to be 7x evaluated from 0 to 1. That's simply 7 times 1 minus 0. That's simply 7. X bar is 1 over m, the integral from 0 to 1 of, along the x-axis, of course, there's x, there's y, and here we're talking about rho times x dx. The 7's cancel out automatically. That is x squared over 2 evaluated from 0 to 1. That's 1/2 into 1 squared minus 0. That is simply 1/2. And if I find y bar, that was 1 over 7, the integral of rho times f of x squared over 2 dx. That is, from 0 to 1. That is a constant, so that's 1/2 times x evaluated from 0 to 1, 1/2 into 1 minus 0, that is 1/2. It turns out the centroid for this problem is 1/2, 1/2. And the reason that is the density is not varying. The density is constant all throughout this medium. Now, what if that changes? Well, that's going to come up in your next class a lot heavier than you like. But it's not as hard as you think. Here we go. We're talking about rho is 2. It's fixed. The region is y equal cosine of x. And y equal negative cosine of x. So basically, there's the region. It is symmetric. Okay, well, let's see how this works. If I want to figure out the mass would be simply the integral from -2 to 2. And the way it works, I'm going to run vertical. That's going to be the top. And the top function is y equal cosine of x. And the bottom function is y equal negative cosine of x. So you take top minus bottom. Cosine of x minus cosine of x is twice cosine of x dx. Times 2 because of the rho, of course. So that is 4 times, and this is going to be the from negative pi over 2 to pi over 2. So that's going to be, what do you take a derivative of to get cosine sine of x evaluated from negative pi over 2 to pi over 2? That is 4 into 1 minus a negative 1. So that is 8, because that's 2. Okay, and when I want to figure out x bar now, can you guess what that would be? X bar would be the integral from negative pi over 2 to pi over 2 of rho times x times f of x. Well, we know the top minus the bottom is twice the cosine of x. So that's going to be 4 times the integral negative pi over 2 to pi over 2 of x cosine of x dx, u equal x, dv equal dx, I'm sorry, dv equal cosine of x, du is dx, and if you integrate, v equals sine of x. So that's going to be x sine of x minus the integral of sine of x. So this is going to be 4 times x sine of x minus derivative of, to get a negative sign. If you take a derivative of negative cosine, you get the sign. Perfect, that works. Negative pi over 2 to pi over 2. So that's going to be pi over 2 times, 1 over m. I forgot that 1/8. So that is 1/2. So pi over 2 sine of pi over 2 is 1 minus cosine of pi over 2 is 0 minus negative pi over 2 sine of negative pi over 2 is negative 1 minus 0. That is 1/2 times pi over 2 minus pi over 2. That is 0. And are we surprised that the center of mass is going to be 0, 0? The only way it wouldn't be 0, 0 if the density is not constant. And again, for practice purposes, how about y bar? Y bar is going to be 1 over m, 1 over 8, the integral from negative pi over 2 to pi over 2 of, and let's see how this works. This is going to work as a rho times 1/2 f of x squared. So the top cosine of x squared minus the bottom negative cosine of x squared dx. That is 1/8 the integral from negative pi over 2 to pi over 2. Cosine squared minus cosine squared is 0, and that's simply 0. And recall, you take the top function squared minus the bottom function. You don't take f of x minus g of x and you square the whole thing. Don't ever do that. So the top squared minus the bottom squared. All right. And if I was talking about one of these, y equal 2x squared, 0, 0, when x equal 1, y equal 2, and y equals 0, x equals 0, and x equal 1. The region between those is right there. So m, first things first, the integral of, and here, if they're not giving us the density, that means the density is 1. Y is 2x squared from x equals 0 to x equal 1. Remember, this is 1, 2 dx. That is twice x cubed over 3 evaluated from 0 to 1. 2/3 into 1 cubed minus 0. That's simply 2/3. If I wanted to find x bar, let me see how much more there is. Should I make another video? No. A few more problems. 1, 2. Okay. I'll set up the last one. This is 1 over 2/3 is 3/2. The integral from 0 to 1 of x times 2x squared dx. That's going to be, the 2's cancel out. 3 times the integral from 0 to 1 of x cubed. So add 1 to the x cubed dx. So that is 3 times x to the 4th over 4 evaluated from 0 to 1. 3/4 into 1 minus 0. That's simply 3/4. So far, it's about right there, about the x. Now, how far should I go on the y? Y bar is 1 over m, the integral from 0 to 1. A row is not there. And it's going to be 1/2 f of x squared dx. And that is 3/4, the integral from 0 to 1 of 4x to the 4th dx. That is 3 times x to the 5th over 5 evaluated from 0 to 1. 3/5 into 1 to the 5th minus 0. That's simply 3/5. I don't know what I wrote over there. 3/5 is, oh, about right there. All right. Now, another problem. The region between y equal radical x, this is y equal radical x, and y equal natural log of x. This is running up very slowly, but we're going to cut it off between x equal 1 and x equal 4. If I really wanted to graph this properly, the log is growing a lot slower. Okay, well, how does it work? I know what m is. M is the integral from 1 to 4 of the top minus the bottom. and that's going to be uh, that's going to be x to the 3/2 2/3 minus x natural log of x plus x evaluated from 1 to 4. So it's not your everyday problem. Put a 4 in there. Square root of 4 is 2. And 2 cubed is 8 minus 4 natural log of 4 plus 4 minus 2/3 minus 1 natural log of 1, that's a 0, plus 1. So if you plug that in a calculator, you could kind of figure out what that is. And here we're just showing that, look, this is not always your typical problem. Take 2 times 3, 16/3 minus 4 natural log of 4 plus 4 minus 2/3. Now, of course, on a test, you could leave it just like that. Oops, I forgot to close the parentheses. Is there an insert? There it is. It was 4 natural plus 4 minus 2 thirds minus 1. So 2.12, that's what m is. So you could tell that this is going to be a mess. X bar is going to be 1 over m, 1 over 2 point, let's call this just m, we'll put that at the end, the integral from 1 to 4 of x times that, x times radical x minus natural log of x dx. That equals 1 over m times, that's x to the 1/2, 3/2, x to the 5/2, 2/5. And if you let u equal natural log of x, remember when you distribute that in, we're talking about x natural log of x, du is 1 over x dx, dv is x dx, and if you integrate, v is x squared over 2, u times v minus, not plus, minus all of this, minus x squared over 2 natural log of x minus the integral of x over 2 dx. So negative times a negative is going to make it a positive, and this is going to be add 1 to the power, divide by 2, evaluated from 1 to 4, whatever that gives you, 1 over 2.121489. Put the 4 in. 4, that's 2 to the 5th, 32, minus 16/2 natural log of 4, plus 16/4. Minus, and if you put the 1 in, you get 2/5 minus 0 plus 1/4, whatever that number is. And y bar would be slightly different than the traditional. Y bar would be, you're going to set it up, 1 over m, the integral from 1 to 4, 1/2, times radical x squared minus natural log of x squared dx, and you work that out, and you get y bar. Last problem, we're talking about an ellipse where we move 2 in the x, 3 in the y. but we're cutting this off between x equals 0 and y equals 0. X equals 0, y equals 0. So we're talking about a quarter of it. It's kind of odd they didn't specify. But x equals 0, y equals 0 would be one of those. We're going to assume for simplicity they're talking about this. Believe it or not, math turns out to be the toughest part of this problem, because if I want to solve for y squared over 9 equal 1 minus x squared over 4. Y squared will equal 9 minus 9/4 x squared. And y would equal the square root. Now, I could factor a 9 out, put a 3 up front, 1 minus 3/4 x squared. That would make life a lot simpler. And the way it works, mass turns out to be the messiest of those. Mass is the integral from 0 to 2. And I'm looking at f of x, the 3 up front, 1 minus 3/4 x squared dx. Well, we would let's see. Actually, I should have left the 9 in there. It makes the numbers nicer. My mistake. 9 minus 9/4 x squared, because I could think of that as the square root of 9 minus. I could think of that as 3x over 2, and I could say let 3x over 2 equal the sine of theta. If you remember, 3/2 dx will be the cosine of theta d theta. This would become the integral. Now, if I replace this by the sine, we're talking about, okay, third time, 9 minus, give me a sec. That didn't work out the way I wanted. What do you square to get that? Oh, okay. Yeah, I should have pulled the 9 out. 3, because that's not 1, right? I should have pulled the 9 out like I did. I was right. That's okay. So that will be 3 the cosine of theta d theta. So that will be 9 sine. If I put a 3 sine square, that's 9 sine squared of theta. Factor a 9 out, 1 minus sine squared of theta. So that becomes 9 the cosine squared of theta. That's the square root of 9 the cosine squared of theta times dx. dx will be, if you multiply by 2/3, dx will be twice the cosine of theta d theta. And we're talking about take a 3 out, that is 6, the integral, and that's of course 0 to 2. Okay, it's no longer 0 to 2. Put a 0 in there, you get a 0. Put a 2 in there. 2 for x. So if I put a 0, sine of theta equals 0 and theta equals 0. But if I put a 2 right there, the 2's cancel out, divide by 3. Sine of theta equal 1 at pi over 2. So we changed those limits. Now we're talking about 6, 0 to pi over 2. Cosine times cosine of cosine squared of theta d theta, and we know what that is. And that is 3, 2 divides 6 3 times theta plus the sine of 2 theta divided by 2, evaluate from 0 to pi over 2. 3 times pi over 2. Sine of pi is 0. So it is 3 pi over 2. And the reason I said this is the hard part, let me show you what x bar is. X bar is 1 over m. So 1 over 3 pi over 2 is 2 over 3 pi, the integral from 0 to 2 of x times the square root of 9 minus 9/4 x squared dx. Guess what? If you let u equal this, du will have an x dx in it, and you proceed that way, and there it is. So you could say that's 2 over 3 pi, the integral, and that is the square root of u. And the blue part will simply be negative multiplied by 2 over 9 du, and proceed. And that's a simple integral to do. And if you look at y bar, it's even nicer. Why is that? Because that is 1 over m, the integral from 0 to 2, of what? Of 1/2. And if you take f of x and you square it, okay, it's very hard to write through the side. So this is 1 over 3 pi, the integral 0 to 2 of 9 minus 9/4 x squared dx. Very simple integral to do. And that tells you where the center of mass is, somewhere probably along this path. All right, and there's your homework.